It's my pleasure to be here, and I'm excited about it. I like to do these in an interactive way. I don't know if that's the normal mode.
We like it that way too.
But I like questions along the way are fine. If they put us off on too much of a tangent, I might say let's talk about it later, but you're welcome to bring it up. And I'll go ahead and repeat it for the mic in case you guys aren't mic'd or whatever. I'm not sure if we are. We're good? Okay. Let me start. You get a dose of the world according to Flynn if we start here, so I apologize, but I want to set the stage a bit. I'm a big fan of physics. My father is a PhD physicist. He's retired now. And so I love physics. And what I've learned from physics actually applies to the storage industry. In the storage industry, there are three competing needs. And I do this as a gross oversimplification. You can go into lots of details, but I see these as the three corners to it. One of them is performance. The other one is price. And the last one is the protection of the data. Performance, of course, you want things to be fast. You want things to be safe. And you want things to be cheap. Now, why physics? Because it's the physics of the real world that we live in that you can't have all three of those at the same time. If you look at how the media works, to make data very, very cheap, you have to have it super high density. You've got to encode a lot of information in a little bit of space. So it's a question of gigabytes per cubic inch. That works directly against the ability to retrieve it and write it very quickly. The smaller you etch it, the more time it takes to put it there and to take it out. So as technology advances, this spectrum gets wider. You know, you would think that storage would have gotten simpler in the last 10 years, but it hasn't. It's gotten more complicated. This dynamic range has stretched as we have advanced technology to do each of these things better. Flash coming on this side and higher density, shingle drives on that side, whatever. It's making this grow to where the difference between price per gigabyte and price per IOP, or total IOPS, is now several orders of magnitude wider than it was. Now, it's not just the media, because we could say here the media, flash, HDD, tape, kind of that spectrum between fast versus cheap. It's not just the media, but it's also the technologies that we use to do it. When you start adding in compression or dedupe, these things make it take longer. They consume time to save space. Now, other technologies like replication end up taking more space to replicate the data and taking more time, but they add protection. Protection I use as a general term because it covers everything from reliability and availability, disaster recovery, or I would even say manageability, being able to do snapshots and stuff. That's protecting you against your own errors or errors of the application. These storage services are really, you could even say, security, protecting you from theft, loss, being offline. To protect the data, you are fundamentally making trade-offs that slow things down and that take up more space. This isn't going to change. The more advanced we get in working with matter to etch things small, the wider these things get. Now, when we look at the different types of storage, where they fall on this spectrum, there's sort of a sweet spot here. And I would say that sweet spot is dominated by SAN and NAS type technologies. However, it's been, just in the last decade that this has stretched much, much wider. You could put in here things like scale-out NAS, but it's stretched with object-based storage and cloud models for hosting data super cheap. I think I just read in the news that Google is selling for a penny a gig a month nearline storage now. And over here we've got flash appliances, or something that's a little dear to my heart, server-side flash. Now the interesting thing about this is each of these technologies, you know, it'd be one thing if it were just different medias and whatnot, but they're not. These are, for example, different ways to connect the data. Here, things are connected over the wide area network, or over local area network, or a storage area network. Or you get even closer, we could put InfiniBand, but I'm not going to put that there. We'll say you've got direct attached stuff that's on SATA, or SAS, or PCIe, or we could get even closer and say on the memory bus. It may not be that long before we're actually addressing non-volatile memories at memory speeds. So the way you connect to it is different. And the protocols that we go over is different. Here you've got these object protocols like S3 and Swift, and we have the NAS protocols like NFS and SMB, and we have the block protocols, most of those in the SCSI world, iSCSI, FC SCSI, and then over here in NVMe. And you could actually say that the VFS layer, the file system layer within the local thing. So this is a mess. It's gotten super complicated, but there's a reason for it all to exist, because you're addressing different points on the spectrum. But this is accentuating to the point of absurdity the challenge that it is to manage data via the storage container that holds it. Today we have to manage data via the storage container. That is the tail wagging the dog. It's funny because EMC, back when I was at Fusion IO, used to love to point fingers at us and say, yeah, that Fusion IO flash in your server is nice, but it's an island of data that's trapped there. Now, the ironic thing is, I had customers say, yeah, that EMC SAN is an island of data in my data center. It's an even bigger problem because it's got a larger amount of data. Yeah. It's a much bigger island, but it's still an island.
Madagascar, not Manhattan.
Exactly. Now, what do I mean by managing data via the storage container? Think about it. When you copy data between one container to another, it's not the same piece of data any longer. You now have two pieces of data you have to manage. Well, if I'm in the business of managing data, it's a pain in the ass if every time I move it around, I've got multiple copies of it. Remembering which one's which and all of that is a pain. So you end up making the problem worse when you have to manage it, because your data, its identity is only present within the container that holds it. Now, what have people done to try to solve this? Well, the first thing, the storage virtualization. I'm going to talk about this for a minute because I want to draw a strong contrast. Again, raise your hand, ask questions, tell me I'm stupid if you want, or whatever. Storage virtualization. To me, that is how to make a bigger container from a smaller container. We can talk about, for example, building a bigger SAN on smaller SANs. What's a product in that category? How to make a big SAN out of a bunch of small SANs. Okay, come on guys. I need some interaction.
Bplex, SVC.
Bplex, or SVC from IBM,
or
right?
Invista.
Okay.
No, nobody ever made that stuff work.
You need to go now. You need to go. I'm sorry.
Okay.
Tried that once.
Storage tank.
How about NAS on NAS?
We're the other kind.
Making a
That's
bigger
not
NAS
NAS,
out of a bunch of
that's
smaller NAS.
Oh, so we're going to go all the way to a Copia?
We could say a Copia, but you would also say that scale-out NAS or cluster mode NetApp, or auto mounter and grafting together a bunch of different mount points. That is actually the predominant way people do it. And why a Copia failed is because most folks, they just find it easier to set up auto mounter, and then it doesn't put another bump in the wire that kills the performance. Because one of the things about all of these, scale-out NAS and cluster mode, most of these, they do their work by putting a MUX, something to route the data, out front of them all. which just kills your performance. So again, you're compromising now to try to get more manageability, to try to get the ability to span this stuff. You're adding stuff that slows it down. Now, this is, it continues object on object.
Or Swift, object on file.
Yeah, object on object is, let's see, is Viper, right? A way to mux
Viper's
a bunch.
object on file.
Object on file, but I understand they can mux together lots of, and again, it's by putting a box in the middle to do it.
No, they don't.
Fundamentally, this is taking a bunch of smaller
You're believing what EMP
storage containers and making a bigger storage container. So this, it doesn't really solve the problem. The real question is, how do we elevate the data so that it can transcend the boundaries of the silos? There are three key pieces to doing that. Now, the first is to separate the metadata, the information about the data, the identity of the data. Think of it as the directories, the file names, the access controls, everything. To separate that from the actual data objects itself. We have to remove the metadata from among the data so that you can have continuity of identity no matter where the data lives. So separation of metadata from data is the first key. The second key is to take your routing function and remove the routing function from within the storage array. The storage array usually routes the data to this tier, that tier, or the other tier, routes it internally to the different media. What you have to do is pull that routing function up and put it into the client. This is what we call the data hypervisor. Its purpose is to defer to the metadata service to determine where the data is located and then route the data directly to the final destination. This way you get rid of needing to have bumps in the wire rerouting the data because you've pulled the routing function out from here and put it up.
Yeah, but it means I need agents, and agents are evil.
The agent is the NFS client. With the extensions for PNFS, it has the ability to do that routing there. And this has already been pushed upstream into the Linux kernel. So for the first time ever, we can take the routing function and put it where it belongs. Now, why is it so powerful to put the routing function in the client itself? Because now I can route the data even to local media, including local media on RAM bus or PCI Express.
Thought you might like that.
So this is the second key, is the data hypervisor and the routing function. The third is the data moving. And these are agents that live in the network. They could be co-located in various places that are responsible for moving the data when needed between things. The metadata, the routing and the moving, those are all functions that used to be inside of the container and why the data was trapped there. You pull these things out and now you can project the identity and existence of the data across any of these. So this is the fundamental part of the technology, is to turn the traditional storage container inside out by taking those functions and making them external services that are agnostic to the specific protocol, media or technology behind it. This isn't all that it takes, though, to make it work. Fundamentally, once you have made it so that your data can exist anywhere, now you need to be able to choose where to place it and manage that. And this becomes a problem unless you enhance the client to get the feedback loop. So something that we have done recently is push into the standards body enhancements to the NFS protocol to get feedback on performance and such. So for the first time ever, you have a storage protocol that's actually looking at end-to-end response times, throughput, etc.
Okay.
And this gives us the ability to know what performance we're getting.
So can I just ask one question there?
Yes.
You haven't really sort of touched on what format the data is in your triangle, and I think we know it's various flavors of data, although it's NFS to the client.
So, yeah.
Isn't there another angle there around locking and protection and synchronization of the data that's sitting in those lower layers compared to the ones that are accessing it at the higher level?
Not sure I follow the question exactly, so let me go into it a bit and then maybe you can refine it for me. So what we are doing here allows us to do file on file, in other words, using NAS systems as storage containers, file on block and on object, and on top of direct attached storage as well. In other words, each of these technologies, we can project file on it. Now with this, you can do block in a file. In other words, have the system mount the file as a block device and use it as block storage. The name resolution just identifies which LUN you're talking about, because it's a LUN in a file.
And all of that is built into the PNFS client?
Yeah, and even do object and things like showing up as HDFS or other clientless access from here, where it doesn't have to be mounted. So this gives us universal. This is a universal storage switch. I'm consuming storage of any type. I'm elevating it to the highest semantic level of a file system with all of the access controls and niceties here, but then able to present it at any of the raw levels as well, at object or block. Now, I don't know if that quite answers your question.
Not exactly. So the question was more, you've said file on block, file on file. What's to stop, or what's protecting a client that isn't part of the schema coming in and accessing the data that's sitting on the lower level? Two clients that are accessing the same data,
right?
How do they communicate with each other?
It's presumed that to get access into this global data space, that you have to access it through the data hypervisor.
Okay, so the data hypervisor is going to own all of the storage.
The data hypervisor is the agent that's built into the OS or other location, which has the universal protocol switch. That routing function knows how to defer to the metadata service to get the correct route. A good example of how this works.
But if,
that gives the routing, but it doesn't give any locking. It doesn't give any protection of accessing that data concurrently.
The locking is done in the same way that it is in the NFS protocol. Of course, block devices don't have any locking, so if you're mounting a LUN, there is none, and that's done at the application layer. Which is mostly the case for very high-performance apps, is that they do their own coordination.
But if I'm doing file on block, the application is seeing a POSIX interface, and it's going to make a request for a lock.
That happens through here. So this is serving NFS SMB and is doing the range locking that's available there. Very high performance applications.
Okay,
like
so the metadata is very fine grained.
For the locking function, yes, if you're using the locking function there. Many applications like Oracle go O-direct and they coordinate themselves.
So I might have missed this, or we haven't gotten to it yet. At what level is this abstraction happening? So it sounds like we're saying we're using the native NFS client with some enhancements that you guys are suggesting
actually, they've already been adopted in the standards body. The PNFS, parallel NFS, allows for this model of resolving the metadata and then routing the data directly.
So you may get to this, but what if I'm not in a environment that PNFS or NFS as a client access method is an acceptable method?
We can do it with what we call a data portal, which presents the older protocols, but requires an agent to do the translation in the middle. So it can. You
really wanted to avoid the word gateway, didn't you?
Yeah. We don't want to use gateway. Gateways are a sin. So built into Linux, the client is native. Built into Windows, the SMB client is native. And ESX. So it's available in each of these operating environments.
So are you presenting all of this to SMB3 the same way you're presenting it to PNFS?
Actually, I'll go into some details here, but this is patent pending. we're putting a filter driver out front of the Windows native SMB client,
Okay.
which strips away the data accesses and routes them.
Okay.
So SMB thinks it's talking to an SMB server and thinks it's sending all the data down that same wire. We're redirecting those data accesses
So you're building
here.
your own PSMB.
PNMS front into it, and without even having to modify the SMB protocol. We just trap the data requests before they go into the native SMB client.
Okay. The concept of file with no file system is...
Well, here's an interesting point.
Because if you're doing file on block and you're doing redirecting, the traditional concept of a file system seems to have fallen out of this whole thing.
we take the concept of the file system
And you're
we
managing
add
it in the
on
metadata
side
servers,
so that you don't get in the data path. Because here's what's broken about storage today. All storage today has the data and the metadata mixed, and the control channel and data channel have to go the same way. The same agent that resolves the file foo has to subsequently route all of the data to foo. That would be like if you...
So this is non-von Neumann?
This is as if you go to google.com. You know how it resolves Google to an IP address? Can you imagine if the DNS server had to proxy all of the traffic to Google just because it resolved the name? That's how storage is broken today, and why file is smaller than or slower than block. File is slower than block because the control channel is more sophisticated. It's doing file names and so forth, and it's doing that in the data path. The only way to fix this is to take the metadata and the control path and split it off to the side and do a DNS-like resolution to a route that can then go directly.
So if I have to speak block, there's an option to block to file. And in my mind, the only way to do block to file is via a gateway, which is a SAN.
No, block to file is actually rather easy. It's like a loopback device on the operating system. He takes a file and mounts it as a block device. So when he opens a file, he's attaching to a LUN. And the interesting thing is this can happen even if that is on a real SAN. So what happens is I've got a SAN here with a bunch of block space, and a file name, say foo, is saying I'm sitting here and I'm this block range. Now on the client here, he says open up foo and make it look like a LUN, a block space for me, so that my app can use it. Then it turns around and maps that block space, and when it talks to it natively over Fiber Channel, just as fast as it did before. But it had all the convenience of resolving the name in a hierarchical namespace with permissions.
Is a byte range, not a LUN.
It's not a LUN now. Now it can be a byte range. Okay. And I can snapshot it and other things within the same space. And I can move it.
Whoa, 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 whoa.
Let me talk about how data moves, because this is actually one of the keys to the whole thing.
Yeah, we're coming back to snapshot, though.
We'll come back to snapshot. But first I have to go to move, because the way things move is that one of the other cool things about this parallel NFS is you can route the reads and the writes separately. And you can route the different ranges separately. So we can put an agent in the middle that is responsible for copying the data from one container to another, and have that agent coordinate with the stream of writes that the application is making to make sure that those writes get reflected even in the new copy. Reads are going directly. Once he's done, reads go directly to here. Writes, meanwhile, get split so that he can make sure that all of the new things written go here. That same technique, by the way, can be used so that it can make a point-in-time snapshot even while the data is being moved and written to.
So in your previous example, you said, hey, we're going to mount foo as a LUN, essentially, and PNFS goes and performs its lookup, etc., and finds the range of addresses, range of blocks where it'll exist. And then you said present it over Fiber Channel. That's the part I'm confused on.
Present it to the application as a block device.
Yes.
That's just a matter of in the OS.
Right. Yeah, no, I get that. That's what NetApp's been doing forever, so that's
the way the PNFS, this universal protocol switch, the way it works is the MDS says it's found on this SAN, this LUN, and this byte range. the client then attaches to that LUN over fiber channel and talks at that byte range.
Yeah, that's just PNF.
But isn't that what it would be doing if the not gateway didn't exist in the first place? It would have just simply gone there?
Except for you wouldn't have had the convenience of a namespace and the ability to think of that LUN as a file within everything in the same data space.
It's not inconvenient necessarily at the moment. I mean, you give me some examples where we get into the extra layers of convenience, because I'm not actually seeing how it's better yet. Some of the other stuff, definitely. Yeah. But in the case of presenting
give me
fiber
just this
channel
much
as a
and I'll be
file.
happy. Give me this much and I'll be happy, and that is that it doesn't get in the data path and it doesn't decrease performance. That we are at least routing it the same way it was before. Ultimately, it's going directly over fiber channel with no data having to be copied over other layers in the network. If you'll give me the fact that I'm not slowing down that direct FC SAN access, then what I'll give you is that I've extended it now so that I can talk about that thing as a file within my namespace, and I can perform other operations with it, like migrate it to different places when it changes its characteristics. So example, I can say, okay, this LUN, no longer active, I'm going to archive it, or I'm going to make a snapshot of it and I'm going to move it into the cloud, take it offline. You can't do that.
But let's say the LUN is active and I want to move it to a different tier of storage. Is it going to maintain a dual stream between the two, present the new location,
it's able
and do
to
a block swap essentially, and now it's going to then terminate the old one?
So I can move it from SAN to NAS.
The data mover is temporarily in band, right?
The data mover sits in band on the write stream to make sure that those things get reflected while it's moving, and it can do this on a windowed basis.
And it constantly updates the metadata server to know, so that we know what's been changed.
So we call it a sliding window. Okay. So if we look at the full extent of the file, right, it's trying to make a copy of it while at the same time the application is writing things. So we slide a window, and that window has this proxy in the middle that's making sure that the things get replicated. This window can keep the impact of having a proxy in the middle rather small, while the stuff routing.
Now, is that in-band proxy also required for the snapshot?
The in-band proxy,
because if you say snapshot of a byte range to
so there's two ways
block storage device, it's going to say, "Are you nuts?"
Yeah, there's two ways that we do snapshots.
Okay.
One way is to leverage snapshot capability within the storage device itself,
which requires that the device's snapshot granularity be the same as my data granularity.
Right. So if it's a NAS system, then our objects are objects on the NAS. And we can use
but most NASs can only snapshot at the volume, not the file level.
We're using the clone, the file level cloning capabilities there.
Which most NASs don't actually have.
To do a snapshot, we don't actually have to talk to these guys until something goes to be written. And that's the second method, is to use this model of having a proxy in the write stream so that we can preserve a point in time while allowing modifications to occur.
Do you have your own snapshot technology as part of it? When I think of how it compares to VPlex and others, if I'm going to move, if I move a NetApp snapshot to a VMAX, it's like, I don't know what this is. I mean, I have no idea what's going on.
Let me see if I get this right. So the metadata server keeps. So I create a clone. More complicated case, read-write snapshot. The metadata server keeps track of which blocks exist in the primary and the clone, and coordinate with the proxy to make sure I get the right ones?
Yes and no. We've worked very carefully to not have the metadata service have to work at block granularity or anywhere close to it, because that would overwhelm him and make it not scalable. Because then you need a big server for that, yeah. So the way the metadata server works is he does the snapshot, and it's completely a figment of his imagination until any given object needs to be modified, and then it does a copy on write. Okay. It sets up the copy on write by putting an agent in the middle that can perform the copy on write.
That does the actual work.
Right. Yeah. But that's only at the point in time when it goes to get modified.
Okay.
Yeah. 5 minutes. Okay. All right. So let's jump to the net of all of this.
And the metadata servers are a scale-out cluster, right?
Yes. We're starting with something simpler than that, and I will give you a bit of a clue on this. because we're using some cool technology here, and that is, instead of a traditional file system or whatnot, this is using scalable key value store capabilities to store the inodes and D entries, etc. But one of the most important parts of the system in the last few minutes that I have here is to recognize that file systems were born in an era when storage was flat and there wasn't the dynamic range. But if you look at the data itself, I've heard estimates say that 80% of the IOPS that hit primary storage are to files that don't even need to persist, don't even need to be there if you were to crash and start again, the temp, the scratch, the swap, etc. So 80% of those IOs should be handled by systems that are further on this end of the spectrum, like server-side flash. It was hard for us to convince people to put it there because they couldn't manage it. So they put all the files on their primary storage, even though many of those files had no reason to be there. They weren't needed after a crash, a restart. On the flip side,
the similar stat I've heard is that upwards of 70% of the queries to file storage are for only metadata. You open that folder.
Well, that too.
And so that same idea of
and
moving the metadata
exactly.
closer to the client would be improved there.
Exactly.
As well.
And the other thing I've heard is that if you look at primary storage today, something like 70–80% of the capacity is occupied by files that aren't used, that they haven't been able to destage because it's such a pain to have to pull it back, because when you switch protocols, to pull it back is a pain in the ass. So you're saying 80% of the capacity should be escaping from this prison that is the storage silo, and 80% of the performance IOPS should be escaping from it too, but they can't, because you can't manage data spliced across different silos. So the first benefit of virtualizing the data is utilization. What's interesting is this is the main thing that was VMware's door knocker for getting better utilization of those underutilized CPUs. We're getting better utilization of the storage resources.
Some of us are old enough to remember when that was the pitch for SANs.
The second one is manageability. Now that's actually what really stuck with VMware, was once you had the leverage of virtualized servers, you could provision and deprovision and manage servers like never before. That's the same thing here. Now that you've made the data orthogonal to the application, you've actually, or to the storage, you've actually decoupled the application. Consider the fact that
EMC's going to love that.
Yeah, consider the fact that today your application is bound to the data that it's using, and the data is bound to the storage. If you take the storage offline, the application has to be offline. I've talked to banks who say they have to schedule storage downtime a year in advance because they have to take the applications offline. With this, you don't have to, because we've decoupled the data from the storage. Now the app is decoupled from the storage. So managing becomes a totally different ballgame. This gives you much more leverage on your staff. Now, these are the same two benefits that really, yeah.
The point of view of performance, the MDS has to be very fast to answer your requirements. So, what technology are you using?
Well, from my background, one of the things that we recognized was that Flash gives you the opportunity to pull the metadata and distill it because of the performance density that Flash offers. So we're using NVMe Flash for this. In the day of disk drives, you wanted the metadata with the data to economize the limited IOPS. With Flash, you actually want to separate them.
Sorry. I understand that probably the MDS is a very fast machine, but on top of that, you need a software technology to manage indexes or whatever.
That's right. That's where we're using key value store technology, so we went out and hired the Linux kernel maintainer and most of his team for the Linux kernel NFS stuff. We're actually building something here that's going to be fastest in the world at serving metadata. that'll give us that scale. The beautiful thing is, because we've separated metadata from data, we don't have the problem that most traditional NAS systems do. How much of their memory do they dedicate to caching metadata versus data? And that causes customers big pain to have metadata squished out by data caching, or data caching squished out by the metadata. Here we separate the two and they can scale independently. Okay, VMware, when they virtualized servers, this was their door knocker, and this is what made them stick, because admins got so much leverage on it. But the thing that's different is that in virtualizing the server, you had to sacrifice performance, because we had to introduce a layer of indirection between the operating system and the hardware. That hypervisor is like an OS under the OS, and it killed performance, especially on I/O related tasks. The amazing thing about this is that we are actually removing a layer of indirection in the network by splitting the metadata off to the side, allowing the data to be routed directly. That's no better exemplified than by having server local media being accessed natively over the VFS layer. So we can put server local media. Let me emphasize this. If I have enough time to make a small tangent, I want to show you how powerful the technology is. So let me talk about it for just a second. Let's suppose that you don't have any shared storage, and all you have is server local storage. That server local storage we can virtualize and export as a pool of storage. When it's being accessed by the server itself, it's accessed directly. No protocols involved other than going through the OS to access it. If a neighbor, somebody else is accessing it, then it'll go over the NFS protocol. But all of that server local storage can be pooled together. That sound familiar? Hyper-converged storage? There's a very, very big difference though here, in that this is happening at a higher semantic level and allows us to place whole files on the server that's actually accessing them, and to place their mirror. I should have mentioned that. Sorry, nobody asked the question. You guys are slacking. You're supposed to ask about reliability. Because we've added into the hypervisor not only the technology to do snapshots independent of the underlying system, but to do replication, synchronous replication. So we can mirror the data to multiple data storage at the same time. So
synchronous local replication.
This is synchronous, yeah. In the future, we will do asynchronous DR in the hypervisor too, or in the system. But for now, we're sticking to the synchronous. Okay, so in this world, you're able to create a shared storage pool from among the local storage, disk or flash. But this is significantly more powerful than the traditional model. Name some of those. If we go SAN on top of DAS, direct attached, you've got your vSAN from VMware, you've got your Scale IO, and you've got things like Nutanix.
Elementex.
Now, what all, or at least most of these have in common is they're using a hash-based block scattering algorithm. And what that means is that everybody's data is scattered across everybody, which means everybody gets the reliability of the worst set, and everybody gets the worst performance, because some block from somebody is found everywhere. That's why this will never scale using that approach of scattering everything across everybody. It compromises performance. Now you have to wait for the slowest link. It compromises reliability. If too many are down, you're dead. So let me give you just one example. This model of placing data as whole files based on where it's being used, if you have servers go down in excess of your redundancy, it will generally be the files that those servers themselves were using. So the only thing that's offline are the machines that are actually offline. This allows you to scale the system and get performance and reliability even as you continue to scale.
You can do that heterogeneously across all different types of storage with all different types of access methods.
That's correct.
So there's got to be a policy engine here to
Now that's where the big focus is.
What you get for calling me a slacker.
It's a perfect transition.
It's a perfect transition because once you virtualize the data, the problem becomes setting the objectives on what the data needs and matching those objectives to the characteristics, the capabilities of the storage systems. And how do you manage that and the flow of data? Actually, the way we do it is by modeling an economic simulation, having the different data objects be consumers, purchasing space with different characteristics and modeling that so that they migrate to the right type of storage.
Servers are more rational than actual consumers.
Exactly. So this is a good transition to go into some demos that show what we expect the user interface to look like.
Thank you so much, David.
Okay.